Hi everyone, we are now complete, so we can start the seminar. So first of all, thanks to all of you for joining. Today we'll talk a little bit about the Hydrocracker tuning by using AptiTune. To start the presentation, I'll give a short introduction to myself and to IPCOS. Then for those who are not familiar with the process, we'll explain briefly what the Hydrocracker process exists of. We'll look at what tuning challenges present themselves, what approach we feel is best to tackle these challenges, and then we'll look at a case study, and if we have the time, we'll also have a look at AptiTune itself and how to use it. Concluding, we'll have the Q&A session, so please, throughout the webinar, if you have a question, type it into the Q&A box or the chat box and we will receive it and we'll try to answer it at the end of the seminar. Okay, so IPCOS, we're process control experts. We provide services. Those services are based on our in-depth process knowledge as well as our operational experience with state-of-the-art process control. So here you see our offices and the whole team, the whole IPCOS team together. If we look geographically, then you'll see that we have 3 offices in Europe, but we're also present in the Middle East and India. But mainly our activities, they span all across the globe with a focus on Europe and the Middle East. If you look at our different activities, which you can also find on our website, as I mentioned before, we are an independent services provider, so we provide services for any type of DCS, as well as any type of advanced process control software. We do studies and audits, we do PID tuning, all the way to complete ARC configuration in the DCS. We do advanced process control, and we also provide a lot of training. Apart from that, we also have our own technology, which is called Inca, which is a full APC suite, as well as 2 PID tuning packages that you can find more about on our website. Finally, to conclude this introduction, you'll see here a list of our customers, and a lot of these customers we have repeat business with, indicating that we do provide the value that we promise. Before I start, let me introduce myself. So my name is Frederick Motte. I'm a chemical engineer that joined IPCOS about 5 years ago. So I've been working as an APC or advanced process control engineer with the company for 5 years. In this time I've been blessed to work on a lot of interesting processes, and Hydrocracker is just one of them. And this is what today's topic will be covering. So, as I promised, let's have a look first at the process itself. A hydrocracker is actually a catalytic conversion of different heavy components. Typically, the feed will be a gas oil type of feed coming from either the vacuum unit in the refinery, could even be gas oil from the atmospheric unit. And those components will be cracked to lighter components, including LPG, naphthas, diesels, and jet fuel. And this conversion is done in the presence of hydrogen, and that means we'll have 2 types of reactions. We have hydrotreating reactions as well as hydrocracking. So let's have a look at a simple flow diagram, which is shown here. So our feedstock is going to come in, and first of all it's going to exchange heat with the outlet of my reactor. So we'll preheat the feed, and then we'll heat the feed further in the furnace. The outlet of the furnace is then fed to my first reactor. Typically, the first reactor will take care of all the hydrotreating reactions. That means sulfur removal, nitrogen removal, as well as saturation of aromatics in the feed, amongst other reactions. And then in the second reactor, we'll mainly have our cracking reactions, which is actually the reactions that add the most value to our unit. Second important part is that we'll have intermediate addition of hydrogen inside my reactors. So this is where my reactant hydrogen comes from. It's not only adding hydrogen, but it also has an impact on the temperatures in my reactor. Why is that? Because all of my reactions, they are exothermic. They are very exothermic. There's a lot of heat generation, and we risk having runaway. If we don't add this cold hydrogen, we can risk runaway. So each reactor bed will add and add and add more heat. And if we don't quench with cold hydrogen, we risk of losing control of our process. This whole reaction is done at a high pressure. Typically, a hydrocracker will run around 200 bars. We have our heat integration. So as I mentioned before, that output of the final bed is used to preheat the feed to the furnace. Because we are generating that much heat, we try to recuperate as much as possible and save on fuel gas in the furnace. And finally, we have the hydrogen network. There, the stability of the header is important. The header, there's different configurations that are possible. Hydrogen can come from offsite, from an external provider. It can be hydrogen that is generated inside the refinery, for example, by itself. So the hydrogen network, we'll talk about it, but for the purposes of today's presentation, we'll consider a bit out of scope of what we're trying to explain here. So this is for the process, very briefly. Now, if you look at the challenges that we encounter, on the next slide, well, first of all, because of this runaway, it is difficult to test all the loops in open loop. This is important because for tuning, typically you will put your loop in the manual mode, you will step the outputs, and with the process response, you can calculate some tuning. Especially with AptiTune, for example, the feature-based tuning, you need this model to come up with the good tuning. But here it is difficult because we cannot put all the loops in open loop at the same time because we don't want to risk that runaway. And second of all, there's a very important interaction between the loops. If I go back to my process slide, you see that all my temperature controls on the beds, as well as the temperature control at the outlet of the furnace, they are all in series. Okay, so each of the different temperature controllers, they will interact with each other. Because what the first controller does will be seen by the second, that one will respond to that, third one will as well, and so on. So this is a very typical case of interaction between loops. There's also a hidden interaction between the loops on the side of the hydrogen network, because typically all the quench flows, they come from the same network. So also there, some interaction is possible. Imagine you increase the flow on one of the quenches, then you'll see the pressure on the header will drop, and all the other flows will see that and will typically will be reduced if they are not controlled. Third challenge we see is that instrumentation can be limiting as well. Two things to mention here. First of all, if we could build a cascade from temperature controller to hydrogen flow to the flow valve, that's typically beneficial. I'll explain why. But that's not always possible. It could be that safety policy or a HAZOP has indicated that you need redundant measurements for hydrogen, because imagine hydrogen measurement going through the maximum or going to the minimum because of an input open alarm. Definitely possible. Your controls will respond to that, and you risk just cutting all the hydrogen or adding too much, and you risk either runaway or just killing all the reactions. So that could be one reason why that is not possible, and then you have to just build a temperature controller to the hydrogen valve. The second issue with instrumentation can be the valve accuracy. Let's say, for example, if your maximum accuracy is 1%, then you can never tune better than that 1% flow. or what the flow that corresponds to this 1%. You can encounter some stiction, which will also make it hard for your tuning, and also the valve characteristic can be problematic. On the next slide, I have shown two examples. The left example shows you a very typical case of valve stiction. So what is shown here on the x-axis is my valve position, on the y-axis is the measured flow. If I open my quench valve, I move along the x-axis, my flow does not change. All of a sudden, after all this move that has accumulated, I make maybe 2 or 3% in total. Only then I see my flow changing, and suddenly I get maybe 4 to 5 tons of hydrogen extra. The temperature controller will see a sudden drop in temperature. It will start and steer back my valve position. Again, I have to accumulate a lot of moves, and again when I go over a certain threshold, which corresponds to my valve stiction, the hydrogen flow falls back and I'm now back at the beginning. So a typical hysteresis case of valve stiction. This will make my life difficult for tuning. Second characteristic is, or second figure shows a valve characteristic that is non-linear. So in a certain range I have a nice gain between moving my valve and getting more flow. But this actually saturates to a high value, typically maybe for a valve you could see that at 85 or 90% you don't get the same amount of flow. And obviously when I try to tune in this region, I will have completely different behavior than when I try in this region. So before I start, I actually have to look at my valves and I have to do some analysis. So let us look at the approach we'll use, and there we'll exactly start with this kind of analysis. One thing I'm interested in, of all the 5 beds, which bed has the best performing quench valve? Which valve has a characteristic that doesn't look like this, but shows a very nice linear correspondence between valve opening and flow? That would be ideal. Second thing I already talked about, is my hydrogen header stable? So what I should do is just step one of the quench valves, see the response on the hydrogen header. Does this lead to oscillations? It's a typical indication that my tuning is not ideal. Does this not lead to oscillations, but rather to a very slow time to steady state to get back to my original pressure set point? Is another indication that I could improve my tuning. So this is something that should be done first. Then the question about, can we build hydrogen flow controllers? Is everything there? Am I allowed to build this flow controller? And is my furnace tuning up to par? That's also an important thing. Does my furnace, does it reject disturbances that come from feed composition, that come from fuel gas or fuel composition? Does it actually reject disturbances that come back from the preheat? As we mentioned before, my outlet is exchanging heat with my feed. So is it able to reject that disturbance? One question I should ask myself already, is it possible and is it worthwhile to add a feed-forward contribution on the furnace? What this means is, for example, my inlet temperature might vary. This will undoubtedly have an impact on the outlet temperature of my furnace. Is it worthwhile to add this as a feed-forward contribution? Do my process dynamics allow it to be built? So these are all the types of questions you should try to find an answer for before you actually start the tuning. Okay, when we then go look at the tuning itself, the tuning effort that the engineer needs to put in. I already mentioned that it's difficult to open loop test. It's not impossible, but typically operators, they will not be very comfortable with it. And it's also not something that typically IPCOS would recommend, just because of the issues, the safety issues that have been touched on before. So that means my full open loop model matrix, so the full matrix from first bed to all the temperatures, second bed to all the temperatures, even furnace, all those models, they cannot be found easily because I will not always have everything in open loop. The implication of this is that one of the main features of AptiTune is multiple inputs, multiple output tuning. They cannot be used readily because I don't have the full model, so I cannot use those features. So in this case, actually, the control engineer, I have to manually deal with these interactions, and I have to always keep this in the back of my mind when I'm tuning. Okay, so this is something that I have myself to account for when I'm tuning an AptiTune. And this is what the demo will try to show later in the presentation. Okay, if we then focus a bit more on how we do it sequentially. So I already talked about first, make sure my hydrogen network is working properly. And here, because there's different configurations, hydrogen from offsite, maybe I don't have the full control over my header. Maybe I do, then I can tune it as good as I can. So this is an effort that should be done before, but that's a bit outside of the scope of what we're trying to achieve today. So when we're looking just at the scope of furnace and reactor, we first start with the furnace. And here, let's say we just go through the normal tuning procedure. We put the furnace in open loop and we test it by applying moves to the fuel gas flow or fuel gas valve, if that is the configuration. When I try to tune it, it's typically beneficial to use the inlet temperature as a disturbance variable. Because then I can easily or more easily find the nice model between fuel gas and temperature and remove all the interaction that is there between the inlet temperature of the furnace, which might be caused or which might be disturbed by my reactor tuning at the moment, or even feed changes. This is what allows me to account for those disturbances and allows me to actually tune them with a good model for fuel gas. And when I tune now, I should always tune for disturbance rejection. Typically, we are not going to move the set point of the furnace often, or we're only making small moves. Instead, we're mostly interested in rejecting all the disturbances. So you tune for that scenario. Now, when you come up with some good tuning, you validate it in closed loop. And as mentioned before, if my analysis told me that it's interesting for me to build a feed forward, then I can also look at that case. Okay, once you're satisfied with the performance of the furnace, you should move to the reactor beds. And here, once again, I'm using one of the answers of my preliminary analysis. We're trying to test or trying to start with the bed that has the best performing quench valves, because that typically that gives me the most possibilities of tuning with a fast but robust tuning. So what I start here, I put my furnace in closed loop. I'm happy with that tuning. And I move to the beds that I identified as the best candidate. And here again, I just go through the normal sequence of open loop testing. If I have a flow controller, I will step the flow set point. I consider here that the flow is tuned well. If it's not the case, then you should start obviously with the flow controller, but that is typically rather easy. If you work directly on the valve, then okay, we will step the valve in manual. If I look at the position of the other beds, then as much as possible, I would like them in manual, but obviously this depends a bit on operator confidence. And as explained before, I cannot have all of them in manual, but maybe it's possible to put the beds of the second reactor in manual and keep furnace and the two beds of the first reactor in auto. That is entirely possible, and that is something that can be useful to better be able to see the interactions between the beds. Okay, now once I've done my open loop testing, I've made a number of steps that allow me to see a good response. I'm confident that the response I've seen is representative, because sometimes when you have stiction on the valves, you may do a 2% move on the valve and see nothing, and do an additional percent, and then see the full effect of the 3% move I made. If I see this, then I should repeat my steps a couple of times with that 3% to find the correct model gain and continue with this. Now, this best performing quench valve, here I will try to tune it as fast as possible, tune that temperature as good as I can, obviously within the robustness constraints. So I look at typical load disturbances, I look at my noise sensitivity. For example, if my temperature is rather noisy, and I can say for this given amount of noise, I only want my output valve to move by 0.5%. So this is the kind of constraints you'll apply to AptiTune. And then from the results, I take a note, a mental note, or I take a log in AptiTune of the controller dynamics that I wind up with. So why is this important? This is important when we move to the next bed. Now, why do we try to tune this bed as fast as possible? Because this is the bed that will act as sort of a hinge. It will be that bed that is able to decouple the interactions between the different beds. If I have a disturbance coming in, this bed that is tuned fast will reject this disturbance as fast as possible and avoid that this is not handled, and then it goes to the next bed and the next bed. And each bed will add a little bit of action, but will never reject the whole disturbance, and you see it back at the inlet of your furnace, and then you're kind of in a loop that is self-sustaining, because every time you see an output disturbance coming back to the inlet, my inlet cannot take care of it, and so on. So this is the kind of this is the bed that will kind of decouple the whole inlet or outlet to inlet disturbance. Once I've done this, I will test and tune the other beds. And here, when I'm tuning, I need to make sure manually, as mentioned before, that the tuning does not interact with the beds that we already tuned. So typically this means you'll have to impose some kind of constraint while tuning to make it slower than the fastest possible tuning that you would typically find. Okay, important to note here is that this is all done before I'm actually moving back to the DCS and entering my new parameters. Okay, because typically what you see is that the existing tuning was found not to be performing that well or not optimal. And if you change only one of the beds and you don't take into account all the other beds, you might actually make it worse because you haven't looked at the other beds yet. So you should do all the testing first and then the tuning exercise in AptiTune before you actually move to the DCS and test the results that you came up with. Another important note here, again, I repeat, is that we haven't been able to use the full MIMO functionality, so we haven't been able to take into account all the interactions. We may have been able to see some, as I will demonstrate in the demo, but we haven't seen all of them. So that means when we go to the DCS and we apply these parameters that we've calculated, and we've already taken the step of trying to manually make sure that they don't interact, it might be necessary to then do some manual fine-tuning of certain loops. Okay, on that note, let us move to AptiTune. So I will stop the presentation here momentarily and then move to the AptiTune screen. So what I've done here, I prepared some tuning cases. For the scope of this presentation, I've just started with some simple models. So I've skipped the modeling step. I'm confident that everyone knows how to test and tune. So for each bed, I just have a simple bed with a simple model. So if I increase my hydrogen, my temperature will come down. And I've configured some different gains and some different dead times. And when I move to the tuning of each bed, let us take, for example, the first bed. I don't impose any additional constraints. I'm just interested in what AptiTune will come up with. So I give it a go. I see that my parameters, they have converged. And when I look at the disturbance rejection, which is what I'm interested in, okay, this first bed is rather fast, and you see that if I zoom in a little bit, that within 8 minutes, my disturbance will be rejected. And there's a small but limited overshoot when I come back, so temperature dips about half a degree and then goes up by only 0.06 before it lands out again. So very decent tuning, very fast. And okay, if this is my well-performing bed, then this looks okay. I've just used the default parameters. So default gain margin, default dead time margin, which means my controller will still be robust, even if my gain is off by a factor of 3, and my dead time is also off by a factor of 2. In that edge case, I will still have obviously an underperforming but still a stable controller. Now, if I were to do this for the second bed, so okay, I've also tuned here. So I've done the same thing. I haven't applied any additional constraints. And third bed, again, I have the constraints, no additional constraints applied. When I would look at these three tunings, all of them would have, I'm sorry, I haven't run this again. One moment. Okay, when I look at this tuning, also here I will see a very similar kind of response. Even though my model is different, I have a different dead time, I have a different gain. Dynamically, if you look at it big picture, it's almost the same. So between 6 and 8 minutes, I'm back towards my set point. And here it's a little bit slower, it lines out around 10 to 11 minutes. But still, those 8 minutes I saw for the first tuning, 11 minutes here, they are very close to each other. So what I could try to do is, if I had the possibility to test my first, second and third bed together, then my model matrix may look like something like this. So this I've been able to find by open loop testing. Why can't I use the full MIMO testing or MIMO tuning? It's because I lack these models. These models are there because, as you know, you have this interaction between outlet and inlet. So what you would typically find here, but that is very hard to find, is a model that is constant. And then maybe after 20 minutes or 25 minutes or 15 minutes, it depends a bit on the dynamics of your hydrocracker, you will see a sudden disturbance impacting the temperature here, impacting temperature here, impacting temperature here, which will make it difficult. Well, if I don't have these models, I cannot reliably say or confidently say, if I tune it in AptiTune, this will be the best result. But what I can do is use the models I have to do some engineering judgment. So what I can do is just with this constructed model, I can build a simulation case. So in this tuning case, I will not look at tuning. I will only look at one of the features here, which is simulation. And when I go in here, for each of the three controllers that I have, I can enter a certain tuning set or tuning parameters. And I can also apply a different disturbance for each of them. And what is interesting to me is when I apply a disturbance to my first controller, what will be the response of the second and the third beds that are in series? Okay, So what I will do is, first of all, do some housekeeping. I'll close some of all the screens I have open so that I only have open what I'm interested in. So I have my simulation case open. And then I have to check that the tuning I have entered, that they are okay. So let me put the second bed tuning over here. So I have some fast tuning here. I entered this for my second controller. So I find 83, 1.5, and 0.37. And for my third controller, I do the same. I can put this over here. So I still have my overview. For the third bed, I find again a fast tuning. Gain is 35 in this case. It's a bit faster again, 86. And my derivative time might be 0.55. Okay, when I now go and simulate this case, I press the play. And what I see here, and I will do some housekeeping with the curves that I don't need. I haven't applied any measurement disturbances so that I can remove. What I can see here now is on the top curve is the response of my first temperature, third curve is my second temperature, and the third or the fifth curve is my third bed. So what I see here is with my tuning I found on first sight it actually looks pretty good. So each disturbance is taken care of pretty fast. But if I look to it a bit closer, I see that my third bed, okay, this doesn't look too bad, but actually it's very fast. I zoom a bit in, this disturbance, so I'm still looking at this fifth curve, this purple curve. Okay, this first bit is just the inlet temperature that is disturbed, so that's something I cannot help. But then my tuning effort will actually reject this disturbance in about 5 minutes. 5 minutes, that's pretty fast. So you start around, let's say, it starts controlling around the 4-minute mark, and around the 10-minute mark, so about 6 minutes, I've already rejected my disturbance. But my first controller has exactly these kind of dynamics. It's also rejecting disturbances of the 6 minutes. That means that obviously the curve I get at the outlet here will be amplified by my first controller because it will be too fast, it will try to reject it, but the disturbance itself is in the same range of dynamics and it will make it actually worse. So you can't fully then reject the disturbance in the first bed and so on, so you still propagate towards the other beds. I'm looking at the time and I see that we're running a bit low. So I will just briefly show what you can do in AptiTune to make one of the loops a bit slower. And this can be done, for example, when I look at disturbance rejection, I can impose a minimum return time. So instead of this 10 minutes, I might say, okay, it needs to be 15 or 20. So it needs to be slower than the fastest loop I've tuned. And so when I enable these settings, and I tune again for them, and I wait until my solution is converged. If I now look at my new settings, then I see instead of those 6 minutes or 8 minutes I had before, now my disturbance is actually rejected a lot slower. So instead of those disturbances that will now come back to my first loop as a feedback, instead of having those dynamics between the 6 to 8 minute mark, it will be slower, it will be more 12, 15, 20 minutes. And if I do this for each bed, then whatever I do, the first bed will never see those disturbances that it cannot handle, and will be able to be a lot closer to my set point. So this is one way to still leverage all the functionality of AptiTune. So the CISO tuning, but then still using the models I have for a simulation and using that information to fine-tune my results by imposing an additional constraint or forcing it to be a bit more relaxed about this rejecting a disturbance. Okay, so this was very briefly what we have in AptiTune. Let me now return to my presentation. Okay, so what does this mean now in terms of actual results? So when we do the whole sequence of analysis, testing the furnace, tuning the furnace, going through all the beds, then you can see this type of results for example, the best performing quench valve. So here you can see before and after. This is obviously on the same scale, both on the y-axis and on the time scale. Before, there were a lot of disturbances and the controller wasn't able to really reject those disturbances. So you would sometimes come back to set point, then you would reject the disturbance and overshoot and come back and so on. So you would never lose all disturbances. Even though you are stable, you have no runaway, you see that not all disturbances are rejected. While on the right hand side, you see what is possible when you tune each bed with this philosophy. You see that you are able to maintain your set point a lot longer. And what you see here in terms of disturbances is those residual beds that have very bad quench valve performances that will just suddenly add 4 tons or remove 4 tons of hydrogen from the reactor will obviously have a big impact. So this is the kind of disturbance you see from that. But again, it will get back to set point and be a lot more stable and doesn't propagate further along the chain of beds. And what this would mean, for example, for the weighted average bed temperature, typically an important KPI, you see again before and after. Before, this is the compound or the combination of each of the beds. You would see a large amplitude. This amplitude has been cut roughly by 50%. Again, residual amplitude is caused by a sudden movement of a valve that gives you 4 to 5 tons extra. That can never be avoided. But still, overall, we are a lot closer to set point. And what's also interesting is that the period of disturbance or oscillation has been reduced from about 6 peaks or 6 full periods you see here to about 3 to 3.5 on the right hand side, which gives the fractionation unit that comes afterwards a lot more time to handle these disturbances and reject them accordingly and not vent any recuperated hydrogen, not lose quality control, and so on. So this is just a very brief showing of what kind of result this can lead to. So tuning, concluding, yeah, we said that tuning is difficult for a number of different reasons. By firmly analyzing the process and using a structured approach, we can actually leverage the performance of each bed to tune them with AptiTune accordingly. And there is some control engineer judgment required to optimally tune these interactions because we're not able to use the MIMO functionality. And the results show that even for underperforming instrumentation, with the proper tuning, you can actually stabilize your reactors and have a better performance on both KPIs on the reactor as well as the performance of loops in the fractionation units. Okay.
Okay. Good. Thank you very much, Frederick, for this presentation. Gentlemen and ladies, in case you have any questions that you want to raise, please use the chat box, the Q&A chat box within WebEx. So we'll have a direct view here on your questions, so we will collect them and Frederick will answer them. So please go ahead, raise your questions there, but in the meantime, some people already have asked some questions via this chat box. And one general one, perhaps, Frederick, is this tuning approach always applicable?
So in short, yes. Because, yeah, first of all, you do a lot of process analysis. So you look at some historical data and you use your process knowledge to already answer the important questions that I listed before. And those typically, they already point you in the right direction of where should I focus first. And as I said, maybe your hydrogen network is not performing that well. So in that case, that is a quick win. If you can improve the tuning there, improve the control performance there, it will already allow you to make some to make some gains on the performance of the reactor. Then for the reactor sequence, well, each reactor obviously has its own design. It has maybe different residence times. The gain matrix or the gains you find might be different. So even though maybe one quench valve is performing better, maybe the process dynamics there could say, okay, this actually has a slow response. Maybe I have to look at another bed that also has decent performance, but that has a quicker response to temperatures. Then I could use or consider using that one first. But overall, this kind of tuning approach can be used for all hydrocrackers in general, just because you do a lot of investigation and you use that structured approach before you actually start tuning.
Mm-hmm. Okay. A question that just came in. Can you explain how did you build your MIMO matrix model?
I take it that this question is related to the model matrix I showed before in AptiTune.
With the upper diagonal.
Yeah, with the upper diagonal field. So if I go back to AptiTune, so this is the model matrix that I showed here. So these kind of models, well, first of all, the diagonal is easy because these are the models that you find when you just seesaw, let's say, step one bed at a time. You'll just see a response from your hydrogen flow or your hydrogen valve to the bed. So that is an easy one, and typically that response is rather quick because you do it very locally. Now in this case I was lucky that I was able to, after some testing, some seesaw testing, we were able to build some confidence. We saw that the process gains were a bit smaller than we maybe expected at the beginning. So I was able to, or we were able to test one reactor completely in open loop, so 3 loops in manual at the same time. And what you then get is when I step my first bed, I still have this fast response to the second bed, but now I also have the secondary slow response to my second bed, because that one is now also in manual, it's not controlling. So I have an impact there. And then thirdly, I also have one to the third bed. So each time my model gain and process dynamics as well as the dead time will be different. But because I had all of them in manual, I do see this response. What I do not see, as I mentioned before, is I don't see the feedback. I don't see my second bed having an impact through the feedback, through the heat integration to my first bed. This is something I don't see, as well as on the third row. This is also something I don't see from my third bed to my first and second bed, which is there. This coupling is there, but because I kept my furnace and my first reactor in automatic, I don't clearly see this response, or I don't see it at all because I already worked on the tuning of those loops.
Mm-hmm. Okay.
So this is why I cannot use the full MIMO functionality, because actually I don't have the full model. But still I can use this kind of information to build the kind of simulation I showed you before to get some insight into what would happen if I have a disturbance on my first bed.
Yeah. Okay. Another question: what if the best performance quench valve is the one of my last bed? So.
Right. So that would mean indeed that you have that final bed. Let me just show the process flow diagram for ease of explanation. I go back to my presentation. I go all the way back to the process flow diagram. So let's say that indeed the beds I have with the best performance is my last bed. Ideally, obviously, I would prefer it maybe around first or second bed, because yeah, then I can just reject the remaining disturbances that the furnace has. But if it's the last bed, it's not that bad. I will still try to tune it as fast as possible. What I have to keep in mind though is that maybe my first bed of the second reactor or my second bed of the second reactor has a very bad performance. So maybe the disturbances I see on my third bed are really big. So I have to make sure that I don't tune it overly fast, because I would be chasing my own tail then, and I would be able to reject everything. But say this is not the case, then it's actually not a problem. Then I just tune it as good as possible. That would mean actually that the disturbances going the inlet of the furnace will be minimal. So I will have a rather constant inlet temperature, and that means it's easier for me to tune the furnace and keep the inlets of my reactor stable. So that's one way of looking at it, is saying, okay, maybe it's the last bed, but because I have kind of a circular loop, it doesn't actually matter where I start. Now, if in your case my last and my first bed, they are more or less similar in performance, it's probably easier to start with the first bed and then move your way to the end of the loop.
Mm-hmm. Okay. Another question. Yeah. In the meantime, please send us your questions via the chat box. So don't forget it. But other people have done already so. And another question here is, why couldn't I configure a feed forward on the furnace? So
indeed, I mentioned that you should look if it's possible and worthwhile to do this. Imagine, for example, and this really depends on the design of your furnace, residence time of your feed in the furnace, process dynamics on how fast does my outlet temperature change when I change or when I make a step in fuel gas. Imagine that your residence time is really quick. So whenever I have of disturbance at the input of my furnace, I see at the outlet in maybe 3 minutes, let's say, and actually my fuel gas has a time to steady state of more than that, or maybe 5 or 6 or 7 minutes. By the time my feed forward action has executed or reached the full effect, I will be actually already controlling on feedback because of that, and then it will become difficult to make sure that my tuning is still stable and let's say separate the two concerns. If on the other hand they are similar, or if my residence time in the furnace is maybe a little bit more, then it's definitely possible to add this feed forward action to reduce already the action the controller has to take. Keep in mind that you should never enable the full feed forward, because then it becomes very tricky to tune your controller. But maybe, for example, 70% of the effect can be done on feed forward, and then the feedback component can take care of the rest. Yeah.
Okay. Perhaps let's go to the last questions. I have two here. How will your tuning approach change if you can only step 1 TC at a time?
Okay, so then I will still mainly use the same kind of approach that I explained. The only thing that will change for me is that I cannot simulate it in AptiTune, but I have to do it really more like case by case. I have to manually say, okay, my first loop has to be around 6 minutes disturbance or rejection time. Then my second loop has to be at least twice or maybe 2.5 times that. Then my next one even more. So what I would do is manually really separate them dynamically from each other and maybe exaggerate it a little bit. Take a look at what this tuning looks like on the process. And then if I see, okay, there's still room for improvement, I can try to move them closer to each other to improve the overall performance.
Okay. Yeah. Good. And yeah, what if you have nonlinearities in your valves? Well, what would you do with that? Would you linearize them first or not?
So this question is related to this type of valve characteristic. In this case, what I would look at is in what operating region is my valve typically most of the time.
Mm-hmm.
So let's say this is only a very maybe end of run kind of situation, or maybe I'm at the other side of the spectrum at the end of the run. I'm here only at start of run. In that case, I would still focus most of my efforts on tuning on this kind of response. So this kind of tuning or model gain that I see to my valve. But then of course if I have really clear correspondence, if I have a very neat type of process or valve characteristic, then it can definitely add value to add it to the DCS as a linearization block. The thing to keep in mind is that you obviously add some additional complexity that you might want to avoid in the beginning when you're tuning, and when you're happy with tuning, you can additionally add this kind of linearization.
Okay, good. Thank you very much. So that were most of the questions. Now you can still raise your questions by email by sending them to me, and then we will later on answer them, and we will also share all the answers to the rest of the audience. So if you come up with some extra questions later on, please let us know.
Okay, that marks the end of our webinar today. Thanks a lot everyone for attending, for asking those type of questions that show to me that you have the understanding of what we're trying to achieve on the Hydrocracker by optimizing tuning. You can always watch a recording of this webinar. It will come shortly on YouTube. You can also find them on the IPCOS website, and you can find the slides of this presentation as well. If you would like, you can also send an email to us to receive a copy of the presentation. Please send them to mons@ipcos.com. Now in our series of webinars, we'll take a little break now for the summer holidays. We'll be back in September, and then the topic of the presentation will be PID tuning during plant commissioning. So what you see is during plant commissioning, or maybe during unit commissioning or a revamp, there's a lot of activity on site. There's a lot of things that need to be done. Equipment needs to be tested, needs to be validated. Heat exchangers go in and out of service. You see distillation columns that are started and stopped. Maybe new things on the DCS, configurations, I/O testing, and so on. They need to be looked at. But another thing that requires attention is obviously PID tuning. Maybe some new controllers have been built, or if it's a new plant, you just get a set of default parameters in each PID loop that are typically far from optimal, and in some cases they might even be unstable. That instability could even cause additional unit shutdowns when we're trying to start a unit, and because of bad tuning, everything just goes into an unstable state and you have to stop immediately. This can lead to additional delays, which obviously during a revamp or a plant startup you do not want. We have experience with this kind of work. We've been involved in a couple of plant commissioning projects where we assist with tuning of controllers right at the get-go, right when you are taken into service. And this leads to a shorter time of commissioning and more stability when more and more units come into service. How we do this and how this can add value for you and your company, this is the topic of discussion during the next webinar.
Okay, so you will get an invite somewhere half of August to with the exact date. And again, if you cannot attend, don't worry. All these webinars are visible on our YouTube channel. So even the first webinar of about 2 years ago, you can also find there. So please have a look at it. Browse through all the webinars that we have recorded since then. Perhaps there might be some interesting ones that you have missed.
For example, if you would like some more information, AptiTune is typically something you will find during those previous webinars, because today we kind of quickly went over the different steps. If you want some more insight on those, it's something that is already covered in one of our webinars.
Indeed, there's a full demo of AptiTune, which is covered into a very extensive webinar, so please have a look at it. Okay, so thank you very much to all of you, and see you back after summertime in September. And again, if you want to have a copy of the slides, let me know. Voila, so have a good summer holiday, and talk to you soon.